Yeah, so Dr. Sri Sabari is a postdoctoral fellow in the University of Coimbra. Is in Portugal. So he did a PhD in Annam University under my guidance, and he completed some 3-4 years back. But he worked in Annam University for his PhD nearly for 4.5 years as a full-time research scholar. And he also worked on a DRDO-sponsored project. It's basically evaluating fatigue, fracture toughness, and ballistic performance of armor-grade, high-strength aluminum alloy. It's a new grade of material. It's armor-grade, high-strength aluminum alloy. It's EAA 2519. That's the grade of the aluminum alloy. And morning I told, no, we have welded up to 19 mm thickness aluminum plates using our facility. So he is the man who did that work, and he has also did the work not only on the open atmosphere welding, he also developed underwater welding capability, also underwater friction stir welding. He developed a tank for underwater friction stir welding. And he also expert in the modeling and simulation, so like harness mapping, temperature distribution, stress distribution, and microstructure modeling. Now he is working under a well-known professor in the field. It's Professor Dulce Rodriguez. She is a lady professor. We have very close interaction with her. And now Dr. Sri Sabari is working as postdoctoral fellow under her guidance in the University of Coimbra and Portugal. So on behalf of the organizing committee, I welcome. I don't want to take much time to introduce Dr. Sri Sabari, and I request Dr. Sri Sabari to hand over the session. Thank you, Sabari.
Thank you, Professor, for the nice introduction. So, I'm Dr. Sri Sabari, the postdoctoral researcher. Here I'm going to present on the modeling and simulation of friction stir welding process. So the scheme of the presentation involves why, how, and case studies. So first I'm going to discuss about the motivation for this study. Next, we are going to discuss about how we are going to do the modeling of friction stir welding process. This is very crucial because when you are going for some of the experimental testing, for example, if you are going for a tensile testing, we are having a lot of standard procedures. We have ASTM standards and other standards, so it is very easy to do with reference to that standards. But when it comes to the friction stir welding, the method of doing that, it's very complicated, and you need lot of knowledge on different aspects of the procedure. So I'm going to discuss that with a little more weightage. And finally, I'm going to discuss about some of the case studies which I made, which shows the capability of the finite element analysis for the various factors of the friction stir welding process. So the motivation why we are going for friction stir welding process modeling, because when we are going for this, we can analyze the process in very detail, which is not possible using the experimental technique. For example, if you go for the temperature measurement of the friction stir welding process, you have two options. Either you can use the infrared thermographic camera, or you can use the thermocouples. So installation of this setup is costly. For example, you need a data acquisition system for thermocouples, and overall we have very important problem that we won't get the exact values of the temperature because of some accuracy problems. When you are going for the thermographic, you have the emissivity problem. Then when you are going for thermocouple, placement of thermocouple is a problem. So a lot of problems are there. So finite element analysis will make ease of this process. So when you are going for the modeling of friction-stir welding process, it will be useful for selecting the process parameters. Because when you are going for a lot of trials, you will end up in a lot of wastages of material, tool failure, a lot of things. So you can select the better process parameter from the finite elemental results. Then you can analyze the stress, strain fields, temperature, and other things. And then you can tailor the microstructure. By knowing the temperature, stress, strain fields, you can realize what is the end microstructure is going to coming after the welding. Then by knowing this process parameters influence, we can avoid the welding defects. Then we can develop the process strategies for different applications. For example, in the laboratory, we used to go for very traditional types of joints, but in industry, you may have a curved surface, you may have uneven profile. So we can develop different process strategies for that. And we can also use the robots in order to control that. Then enabling online quality capabilities. You know that nowadays IoT is an important factor in the industrial revolution, which is the 4.0, the current one. So by using the friction-stir welding process, you can go for the quality control, this online monitoring, these kind of things are possible. So this makes the FSW to get to the industries in a wide applications. Okay, first thing. So now we are moving to how to do the simulation. What are the things you need to know, or what are the procedures we are going to follow? The very first thing is you should know about what are the contact conditions you are going to apply between the tool and the workpiece. So before knowing what are the models available, first I can explain about the basic contact condition, that is the sticking, slipping, and the third variant is partial sticking and slipping. So sticking is nothing but the material will stick to the tool on certain conditions, and slipping, the material tends to slide over the tool. So when the material is sliding over the tool, you will have the friction. So friction is the main phenomena during the slipping conditions. And when you are having the friction, the heat generation is mainly contributed due to the friction. And when in the sticking, the material is moving along with the tool, where the velocity of the material and the velocity of the tool, the angular velocity is similar. So in that case, the plastic deformation plays a major role on the heat generation. And in the partial sticking and slipping condition, you will have both, where the heat generation will be contributed by the friction as well as the plastic deformation. So this is the three basic contact conditions, and with the different friction models, we are going to achieve these kind of conditions. So there will be a question, what to use? Actually, there is no standard there. If you do a detailed literature review on these aspects, you can find some authors reported very good agreement with the experimental condition with sticking. Some people have slipping. Even the same author at different years, he explained, he concluded that sticking works sometimes, and the same person is saying some other time like sticking and slipping is good, because we have a lot of other phenomena, underlying phenomena is happening under there. So the only suggestion is that you have to analyze all the contact conditions, and with the close agreement with the experimental, we can take that for the analysis. Okay, so this is the sticking and slipping phenomena. So Coming to this, how to adapt in the model, we have the friction models, and we can adapt the friction models. The first one is the Coulomb friction law, which is a well-known one, where the shear stress is directly proportional to the pressure. So this pressure is nothing but the axial pressure, and the shear stress is the function of the friction coefficient. So in the earlier stage of simulation, people use this. However, these have a lot of problems because in this equation you could not find any term related to temperature or any term related to the material state. The reason why I am highlighting this, because the friction between the tool and workpiece is not only because of the contact, the real contact there, it is also influenced by the material property. If you have a softer material, you will have a different friction coefficient. However, people used some strategies to include that by using the temperature dependent friction coefficient. However, the softening in material will not be completely accounted in this Coulomb friction law. So in order to overcome this Coulomb friction law, the problems during this Coulomb friction law, modified Coulomb friction law is adapted, where here the yield shear stress term is introduced, and delta is also introduced. This delta is nothing but the slip rate. For example, if we give the value 0 to here, this term becomes 0, and here you will have only mu into p, which is the same as the Coulomb friction law. So when the delta is 0, delta is 0, then you will have the full sticking. When the delta is 1, when the delta is 0, you will have full sticking, full sticking, and when the delta is 1, you will have full slipping condition. So in this way, you can modify this delta value so that you can achieve sticking, slipping, and partial sticking and slipping conditions. And in this previous case, here initially it will consider as the slipping phenomena. After exceeding this critical value, the normal and the coefficient product, after exceeding a critical value, it considers the sticking phenomena. So another model is the Norton friction law. So in this model, the critical shear stress, the contact stress, is based on the sliding velocity. So this sliding velocity is further influenced by a parameter A and Q. This A is nothing but the material constitutive parameter, which is based upon the flow strength, and then we are having the sensitivity parameter, which is very similar to like strain rate and other factors. So Norton friction law is better in many cases because it is including the influence of the material property on the contact condition. Even though there is some problem, because when you are considering these cases, it is not showing different friction conditions from the tool center to the periphery. Actually, from the tool center to periphery, you will have a different contact condition. These models will not have any functions to represent that. So a modified Norton friction law evolved, where the A parameter is a function of the position. So in this figure, you can see that this A value varies with respect to the tool center axis to the periphery. Here you can see that you are having more pressure in the tool front, so you are having a maximum value of A, and you are having a lower value of A in the tool rear. So these can be accommodated when we are going for modified Norton friction law. And here, by changing the value of A, you can achieve either sticking, slipping, and partial sticking and slipping. For example, if you are using a higher value of A here, you can get a sticking, then a lower value if you make, you can get slipping, and if a moderate value, then you can have a partial sticking and slipping. So this is about the contact conditions. So you can choose accordingly based upon the agreement with the literature or with your experimental condition. Then the next main important thing is the material modeling. So if you are going for modeling of a fusion welding process, the only consideration is like a temperature dependent property, because the material property varies or it is non-linear or linear with the temperature values. But when you're coming to the friction stir welding process, you have a lot of things to analyze, because here you are having the material will behave differently with respect to temperature, strain and strain rate. So you need to accommodate all these aspects in order to make the real material flow behavior. So there are some traditional constitutive model is there, and it is well shows well agreement with the experimental conditions. So we can go for either of these cases based upon the data availability and the accuracy of the model with the experimental conditions. So the first one is the Johnson-Cook constitutive model. This is a well-known model which was very famous for for simulating the hard deformations happening in the various processes like compression test, tensile test. You can go for any low strain test, high strain rate test. So you can go for all the tests with this model. So here the flow strength or the strength is the function of the strain component, strain rate component, and temperature component. So including all the parameters, we can get the exact behavior of the material. So here I showed an example of that, and here C represents the strain rate sensitivity. In Johnson-Cook, they are mentioning in C, and in some other equations it is mentioned in the letter M. So there is some problem with Johnson-Cook when it comes to difference in the strain rate, because in some of the model people are not including the variations of this parameter with the strain rate. So if there is a possibility to accommodate the material property with respect to various strain rate, it will give more reliable results, because these values are not constant throughout these strain or different strain rates. In friction stir welding, we may have a strain rate from like 100 per second to 1,000. Even some people observed like 3,000, 4,000, and so on. So here in this case, see. This data is taken from one of the article, and the author only used the strain rate of this 0.001 per second, which is not this strain rate is not happened in the friction stir welding. Maybe it will happen in like the P-mass region, so which won't give a real result. So these are the mistakes people used to do. So we need to present the values where the friction stir welding strain rate domains, which is the like 100 to 1,000 or 10,000 kind of. So the next one is the material modeling is by the northern half constitutive model. So this is another material behavior model. Here it is mentioned the function of the viscosity parameter and the viscosity exponent, and these are not the direct value. You could not get a direct value of this, because this viscosity parameter will have further lot of relationship, and each relationship have different parameters. With respect to time concern, I'm not explaining much about that. So here the thing is they use this viscosity parameter and the viscosity exponent, which is nothing but like strain rate sensitivity. So the next one is the Shepherd-Wright constitutive model. The northern half and Shepherd is almost the models evolved from the Arrhenius equation. So they have the same origin, but in terms of representation, it is changing. So in the Shepherd-Wright constitutive model is widely used in one where the viscosity, effective viscosity parameter is the function of the effective stress and the equivalent strain rate. Further, this can be calculated from with the use of the Zener-Hollerman parameter. The Zener-Hollerman parameter is a parameter. It's a constant which represents the strain rate and the temperature. So above all, we can also use some user subroutines like you can use the Fortran language to write your own program. Like we have like VUMAT, UMAT, UHARD. So these are all some of the Fortran languages which is highly acceptable in the Abacus software. So if you are going for Abacus, you will have a lot of options by including all the things in the user subroutines. So one of the main drawbacks of this constitutive model, one of the main drawbacks in friction stir welding in modeling is you could not predict the residual stress, because when you are going for thin sheet weld, you may have some of the residual stress which is significant, and this cannot be modeled here because these models cannot, it's not accommodating the effect of elastic strain factor. So it is not possible to go for the residual stress, but you can do all the other simulation. Yeah. So next one is the material modeling. The main one is data extraction. Of course, the data extraction is a very difficult one. So when you're going for searching of the data, you don't go for like directly. Either you can go for the some of the tensile tests or hot compression test or hot torsion test, which was performed by like Glebel simulator. So using the Glebel simulator, you can simulate with different temperature and different strain rate. So these stress strain curves will be used, and the data were processed for this model. Okay, so this is the right strategies for taking the data for building the material model. So the main thing is, I'm coming to the mesh part. So there are two mesh parts, which mesh formulations which are used generally in the nonlinear deformation conditions. One is the Lagrangian and another one is the Eulerian. So let me explain this in a very short way. So in the Lagrangian, the mesh model will move together with the material, and in the Eulerian, the mesh is stationary, which means the mesh is fixed. The material inside will move freely through it. So when you take a model, you will have two systems. One is the mesh system and another one is the matrix system. So mesh system, like mesh, then the matrix is nothing but the material elements. So I can explain this with this diagram. You can see that this is the mesh system. The unfilled circle is the points of the mesh system, and the solid fills are the points of the material. So this material is undergoing, this system is undergoing a deformation. So it is displaced from this point to this location to this location. So when it is moving, you can see that the location of the matrix is changed, and the point is there. So in the Lagrangian, the mesh nodes is moving along with the material. See, so both are jointly moving and displaced to another place. So with this Lagrangian, we can use this Lagrangian for the material which is going severe deformations. But when you are coming to friction stir welding, the deformation it is the deformation is very bigger. So the element distortions will be very big. So you may end up with some kind of mesh related error while using Lagrangian for the modeling the friction stir process. When you're going for Eulerian, so the mesh is stationary and the material can move freely. See here, this is the mesh system. The mesh system is similar in this time interval, the next time interval, and the material is freely displaced inside this mesh system. So this will be good because your material is undergoing a lot of changes here. So this Eulerian is can be better accommodated over there for simulating the material flow. So each system have some problems, especially this Eulerian and Lagrangian. In Lagrangian, you may have some error related to the element distortion, and here in the Eulerian, you will have some lot of remeshing. Some kind of strategy will be happen there, so you will have a lot of computation time. So in order to overcome this, the best of Lagrangian and best of Eulerian is taken together in the arbitrary Lagrangian Eulerian. So which is shown here. So here the mesh is moved. Here the mesh will be moved, and it is not considered about fixing along with the node. So these two can be jointly get using get by using the Allais or arbitrary Lagrangian Eulerian system. And recently people are using the coupled Eulerian Lagrangian. The reason why in this Allais system, even we are having some deformation of the matrix and the mesh system. So here also you may have some problem with related to the elemental distortion. So this cell, that is the coupled Eulerian Lagrangian, will overcome that. Here the tool will be assigned as the Lagrangian and the workpiece is assigned as the Eulerian. So when we are using this, we can overcome such a problem which we faced in the Allais. So here in Allais, and another problem is if the friction stir welding process include a lot of strains, a lot of material flow, you may have some problems, and you could not get the influence of flash. Previously, flash is considered as an unwanted material in friction stir welding, and recently it is one of the indicator to know the material flow and to know the defect formations in friction stir welding. If you have an excess flash without destructing the sample, you can say that you will have a defect inside. So it is very important to model the flash also. So the coupled Eulerian Lagrangian supports that, because in this framework you will have a lot of it can accommodate a lot of strain of the material there. So the flash can be identified or can be simulated with the introduction of this void element over there. This void element is nothing but it does not have any material property. These elements will accommodate the material pushed from the bottom to up, that is out of the plate, which is nothing but the flash, and it is artifact here. Okay, some of the case study I'm going to discuss here. The first one is the modeling of friction stir welding process. Here the objective of the study is to know the influence of material properties and process parameters. Okay, the software used for the simulation is Comet. It is an indigenously made software, and it's a dedicated software for friction stir welding. This is a software developed by a university from Barcelona, Spain. and we use that software for simulating this, and for full sticking condition is used. This condition I used because of based on our my previous trials, which is showing well agreement with the experimental condition, so I stick to that. And the Norton half constitutive model is used for model the material behavior, and the friction condition is based upon the Norton friction law. And these are the dimensions of the workpiece and the tool which is used for the simulation. Okay, so as I told in the previous slide, the main objective is to analyze the influence of material property. So what I am going to do is I am going to take AA6065 aluminum alloy, and I have calculated the material property values, the parameter values from the material, and I multiplied. I'm using some multiplier of this viscosity exponent. For example, I will multiply like 2 into 2 into 3 into 4 into 5. Like in this way, I just changed this viscosity exponent value. So by doing this, I can analyze the influence of the material's plastic parameters. Okay, so that is the idea. So here I lowered the value of mu t. I lowered this value of this mu t so that I'm having a new material B. This is a virtual material. This is not a different grade or something. This is just a virtual material. If a material is having this lower mu t, what will be the results? How the material will behave. So that is the thing. Which can be in future, it can be related with any of the grade. If for example tomorrow if you are having a new aluminum grade which is having this parameter, you can directly relate this result with that material without doing any testing, any material parameter prediction testing or anything. So that is the objective. And in another case, I increase the high viscosity exponent, and here high viscosity exponent and empty. So these are the variation. So since I am increasing the viscosity, which means I am resisting the flow, if the material having high resistance to flow, it represents that these material are higher strength. So C and D are the higher strength material. So these are the parameters varied and showed here. Okay, so coming to here, you can see that this is the equivalent stress for the different strain rate is plotted here. Here you can see that how the material is behaved. See, by changing this viscosity parameter and the viscosity exponent, the flow strength of each material is different. So this parameter is included, and these are the different process parameter is used for the simulation. For 600 RPM, by having 600 RPM as constant, I varied this tool travel speed, and here 400 mm per minute is the travel speed set as constant and changed. So you can see here the simulation results, where you can find this is the advancing side and this is the retreating side. So the advancing side recorded a higher temperature, which is a well-known phenomenon. And here this is the longitudinal section, and this is the tool front end, and this is the rear end. So you can see this a wider, higher temperature region at the tool rear, because this region is undergone welded during the previous instances. So you have a heat buildups there, so you have a higher heat in the tool rear. So these differences in temperature distribution is rightly predicted by using these above conditions. So next, I'm going to check the influence of strain rate. So here you can see that as the tool rotational speed increases, the strain rate is increasing. So the tool action is highly influencing the tool rotation action is highly influencing the strain rate in the material. Whereas while you are changing the tool travel speed, you are not having such influences. when you are coming to the temperature predictions during the higher strain rate, you are having the higher temperature. So as the strain rate increases, we can see that the temperature evolution is increases. So this is a very difficult phenomena which you could not understand or study from the experimental means. So with this finite element analysis only we can achieve this. And you can also see that with respect to the material property, the harder material shows higher temperature because it involves in higher torque and higher friction forces. So naturally it is availing the higher temperatures. And while plotting the relationship between the flow strength and the strain rate, we can see that the higher strain rate, the flow strength of the material will be very lower, which is can be correlated with these temperatures. So coming to the torque is a very important indicator. It is a material response to the tool action. So here you can see that while increasing the tool rotational speed, the torque is reduces, which means that when you are having the higher rotational speed, you will have higher temperature. That's why the material softening will be bigger. So the flow resistance will be lesser, so that the torque will be lower. And when you are having the tool travel speed, and the tool travel speed is having a lower influence on this torque, and when the tool travel speed increases, you can see that the torque will be more because the tool will not be available there to make a complete steering, and it is too fast, so that the preheat zone will be very less, and the preheat zone temperature will be very less also. So you will have a higher torque in this place. So when we are plotting the relationship between the torque and the flow strength, we can find that there is a linear relationship. So the torque or the defect formation will be related to the flow strength. So if you are going for a higher flow strength material, you will have a higher possibility of the defect. So defect, and we can also say that you may have a lot of problem in the tool damage. Okay, and these two have the relationship. Why you are having this lower flow strength have lower torque? Because you have lower because you are having a higher rotational speed there, and you will have a higher temperature there. So everything is agreeing accordingly. So next one is I'm going for modeling of friction stir welding of lap joints. So here I'm not included any kind of separation between that. I just had an approximated model. Here the lines I am showing just for the representation. In the actual model it was not there. So when you are going for the thin sheet of lap weldings, we can either use the tool pin, or you no need to use the tool pin. Since it is a thin material, you can also use these strategies for welding the thin sheets. So here you can find two results, the temperature and the strain. As I explained before, here the advancing side having the higher temperature, and here the temperature distribution is highly limited to the top region of the material, where lower temperature is shown here. And here also, when you are seeing the strain, you have a lot of strain in the outer boundary, because the angular velocity is higher in the outer with respect to the distance. So you have the higher strain there and higher temperature there. And here you can see that there is no strain in the lower or the middle part of the joint. This can be understood by the metallographic analysis. Here you can see that this is the lap joint, and this is the center joining surface, and you can see that it is a little bit not clear here in this picture. You have a straight line here, which means that the joining line is still there without any alteration by the tool steering. So tool steering is happening However, in the pinless tool, there is no material flow in the middle of the material. So this process is also called as tool assisted friction welding, because the stirring is not contributing for joining of material. Rather, it is the joining is made by the diffusion bonding between the upper and the lower plates. So here, with the using the higher magnification microstretches, you can see that, this line remains straight. If the material is flowed, this line will be like zigzag, or this line will be vanished. But here the line will remains there, and the diffusions happen between the top and the bottom. So we can understand this with this finite element results. So the next one is about the defect formations. Here two conditions are compared. One is 600 RPM with lower tool travel speed, and here it is higher tool travel speed. So when you are going, this is a pin tool, okay? So in this case, the pin tool is considered. Here you can see that there are some micropores are seen here in this advancing side. Here some micropores are seen here. And one more thing is, there is an upward material happened in the retreating side. In general, when you are going for friction stir lap welding, you will have an upward flow in the advancing side, and you will have a slight downward flow in the retreating side. That is the conventional thing. So due to the upward flow, you will have a hook formation here, and you will have a cold lap here. But for this case, we have a different mechanism happened here. Here, a upward flow in the retreating side, and you have micro cracks, micro pores, and here you are not having any hook defect. So it is a unknown phenomena. Why it is happened, we don't know. So we went for the finite element analysis. So you can see these animations. The two animations, you can see that here this material is not rotating around the tool, it is just bypassing the tool. Whereas in this case, you can see that the material is moving around the tool. So which means that a sufficient material flow happens here, where here it is not happened. That's why we are having an unconventional material flow, and we have a defect formation. So even with this finite element simulation, we can predict the defect formation. So this figure shows the cross-sectional. So this figure shows the cross-sectional results, where the brown color dots are the markers I used here. So here you can see the upward flow, which is very similar here, whereas you are having an upward flow in the retreating side. So here it is not sufficiently flowed here. So we are having a defect. So in this way, the defect formation is also possible to predict. Next, I'm going to explain about an interesting thing, coupling the finite element results with the statistical models. So when you are talking about numerical modeling, actually the numerical modeling refers to both finite element and the statistical. In both way, the numerical model will represent. But in general, people are thinking like the numerical model is only for the finite element or these kind of simulations. No, statistical is also a numerical. So we can use this common factor together to do some magic. So what are the things I'm going to do here is, I'm going to model the heat generation in the friction stir welding and the tool assisted friction stir welding. Nothing but like the pin and without the pin profile. So along with, I'm going to develop an empirical relation model for predicting the welding temperature. So it is a bit complicated, so I just represented in the flow chart. First, what I'm doing is I'm doing the big data analysis, nothing but the collection of literature. From the literature, I'm identifying what are the tool dimensions people are using to weld. So I'm using a parameter G to combine all the tool parameter. Then I'm using the I'm taking the process conditions or the process parameter used in the literature, and I'm doing the finite element analysis. Then with that result, I'm developing an empirical relationship. Then with that, I'm going to validate with that literature. Then I'm going to validate with the aluminum and steel material experimentally. And these analysis up to here is for the linear welding. And I'm checking the robustness or the reliability of the model for also the spot welding. So let's see that. So nearly 300 papers were collected on different aluminum grades, and these are the parameters I identified from the literatures. And this is the G parameter, and this uses the pin diameter, pin length, and shoulder diameter, and I calculated the G parameter, and I found that people are using the G parameter from 130 to 1100 mm square. So I'm using that G parameter for the numerical simulation, and these are the details of the numerical simulations which were discussed previously. And these are the tool rotational speed which I identified and selected for the simulations from the literature. So from the literature, so here also I made a simulation results of temperature analysis. Here you have a unsymmetry, non-symmetry temperature distribution, so which is very similar to the microstructures. And coming to here, we can see that as the tool rotational speed increases, you have the temperature increases, and similarly as the geometry parameter increases, you have the higher temperature. So this can be related that when the tool dimensions increases, you will have more contact area, more friction, so you will have this higher temperature. So coming to the process parameter and temperature evolution, so here also the shoulder diameter and thickness is compared. So here as the plate thickness increases, you are not having the higher temperatures, only the lower thickness have lower temperatures. This is the reason why when you are using the higher temperatures, the heat will be lost from the contact region or from the stir region, because it is having a higher thick material. So the heat loss will be higher due to the heat conduction. And here you have higher rotational speed, and here you are having lower rotational speed. So on comparing, the higher rotational speed results higher temperatures. So I'm not going to much detail about the process parameter. These are the well-known things. Just I'm trying to convince you to show that this is possible with the finite element. Then coming to the main aspects, the development of empirical relationship. So how I developed an empirical relationship. So here I can show that I use this product of the thickness and the tool travel speed, because these two cases involved in heat loss. When you are having a slow welding, you will have a different heat loss, and if you are going for faster welding, you will have a different heat loss. So these are the two parameters involving the heat loss. So I'm just using the product of that. Then I plotted the temperature. Here you can see that for the different shoulder diameter and for the different tool rotational speed and different tool dimensions, that is the geometry parameter. So first you just consider these curves. So I'm just going for a curve fitting, and this curve fitting is perfectly matched with 1 by root of x. So here x is Vt. So here I made 1 by root of Vt. Then I'm seeing this G, as the G increases, the temperature increases, which shows that the temperature is directly proportional to the G. So I introduce G in the numerator, and the tool rotational speed increases, the temperature increases. So I'm using this G, the omega in the numerator. So in this way, this coefficient of this temperature is predicted. But this is not sufficient to predict the final temperature. So what I'm going to do is, this CT is plotted against with the temperature for different values, and I found that this 590 is a threshold, and after 590 and 20,000 you could not have, which means that this temperature is the maximum solid state temperature a friction stir welding can achieve. So in this way, the curve fitting happens here. With the curve fitting, the equation is derived. So don't get confused about the curve fitting. The curve fitting you will have, like if you are having a straight line, the straight line equation is y is equal to mx plus c. So similarly, this is a curved this is a non-linear one. So you have a different equation. So the CT is nothing but the x, and this is an exponent is nothing but the slope, and this is the coefficient for the fitting. So it shows a good fitting because we have the R square values of 0.88. So in this way, the temperature of the aluminium can be, so these are the different aluminium materials. So in this way, this equation can be employed to calculate the temperature. So the robustness or the reliability of that equation is verified with the literature. So that the dark circle is the database temperature, that is the literature, and the unfilled circle is the predicted temperature with the previous equation. So you can see you have a very good matching with that. And in order to get the better fitting, I also multiplied this KT and this phi value with a multiplier, because each authors uses different measuring technique, different measuring locations. So in order to compensate that error, I introduced that. So now I am going to check the robustness of this model to the spot welding. So when we are going for spot, you don't have the pin. So the pin related terms are removed from these equations. And one more thing is, when you are going for spot welding, you don't have the travel speed. So the term V is removed from the equation. And here I used ds by 10. The 10 is the thickness which I used here, and ds is the shoulder diameter. So why I introduce this is because I need to give more weightage to the geometric parameter. So here you can see that experimental condition, this condition, experimental results, these experimental results were captured by using this thermographic camera, what you are seeing here. So here you can see that the tool rotation speed increases, it is not increasing so much, whereas the shoulder diameter increases, it is increasing a lot. So in this way, in order to give more weightage to the tool dimension, I introduced this term. So here also it is giving good fitting. The surface plot is the predicted value. Sorry, the surface plot is the predicted value, and the dotted plots are the experimental values. So it is perfectly matching with the different grades of aluminum. So now, what about steel? Whether this model is working for steel? Yes, we checked that. Here you can see that the tool diameter increases, temperature increases, the rotational speed increases, the temperature increases. So when you are going for steel, the influences is equal for tool diameter and the rotational speed. So I removed this, the diameter divided by 10. So this is the simplified equations, and I generated a new equations for steel, because the steel, the CT will be different with respect to the temperature. And here that the maximum solid state welding of the steel identified is 1100. And here you can see that the dotted lines are the experimental values, and the surface plot is the predicted values. It is showing a very good improvement. And here you can see that DP600 is a high strength material, so it offers higher temperatures because of high flow resistance, so which were also. Am I audible?
Yes, sir, you are audible.
Okay, I heard some noise. Okay. So coming to here, you can see that this DC05 and DX200, we have some differences. Maybe this the differences in this case, DC05 is because of some error due to the emissivity during the temperature measurement. So we have a misfit here. And when it is come to DX200, we have also a misfit, and this can be related with the coating thickness, because DX200 is a galvanized steel. So in the galvanized steel, you will have a zinc coating over there. So this may disturb the contact conditions. So we got some misfit values in the DX200. So otherwise, the model is perfectly fitting with the experimental conditions. So So I'm not going to summarize the results here because my objective is not to summarize the influence of process parameter or whatever the things, because that is a well-known factor, and I think some of the other speakers also explained that. So my idea is only to show the capabilities or what are the things you can explore from the friction stir welding modeling. So the summary is like FE is an efficient tool to predict the temperature, strain rate, and strain field, which I showed in this my results, and we can understand the material response. So in this way, if you know how the material is respond, you can overcome the problem of defect formation, tool failure. You can reduce the cost involving in achieving the optimized joint. So these are the things. And with the FE, you can develop the empirical relationship with virtual material constants. You can play with the material constants by changing different parameters, so you can find what are the actual parameters influencing the friction stir welding. Previously it was believed that the yield strength is an important parameter, then it is identified like flow strength is an important parameter, then identified strain rate sensitivity is an important parameter. This is only happened because of the finite element analysis only. So because of the with respect to the experimental condition, it is not possible. So you can explore more about friction stir welding process with the FE, and you can take it to the industry. And that's the end of my presentation. Thank you for your attention, and I would like to thank my team members, my professor, Professor Dools, for allowing me to take these results, because some of the results are it's not even published. So I especially thank her in this occasion. Thank you to all.
Stress values with FE modeling.
Stress value. So you're validating what? Stress. I understand stress. Like you're validating with the experimental, or you want to know what is the stress happened there.
Sir,
What you're asking?
experimentally I can predict the strength value for the joint. So will it be possible to validate through simulation?
Okay, so you are not asking about the simulation of the process, you are asking about the tensile test, yes?
Yeah.
Yes, it is possible. You can take the same model and you can do further analysis. You can do an analysis, then you can apply. For example, if you are doing in abacus, you can have two different steps. In the step one, you simulate the joint. In the step two, you apply the mechanical constraints and the loading conditions, and you can simulate it. It is possible. It is possible. This is one approach. The second approach is you no need to go for finite element simulating the friction stir welding. You can simply model a tensile sample. You segment the different regions, okay, and you can apply different material property to different region. For example, strain in the tensile the stress zone, you apply a different material property. The TMS region apply different material property, and for base material you apply different material property, and you can see that also. These are the two strategies.
Okay, sir. Thank you.
Thank you. Any more questions?
Hello, sir.
Yeah, please.
Sir, myself, Amal. Can you elaborate about ALE process once more, like ALE approach? Arbitrary.
Okay.
Yeah.
Okay, so in ALE, give me a second, I'll share. Okay, I think you are seeing my screen, yes?
Yes, sir, I am able to see.
Okay, so here, I think you don't get confused about this because this is very simple. Because what are the things I am explaining
Sorry for
here?
the interruption. Can you go for slideshow mode?
Okay. Okay, sorry. So here, you no need to worry more about this because it is very simplified when you are going for modeling with the software packages. So I explained here in terms of some basic like how it is behaving. But when you are going for model, this can be done with a single click. Like if you take like in Comet or in the Abacus, you can do like in a single click. You just select the material and what is the formulation you are using, just assign it. That's the thing. Okay, so coming to this thing, this alley is taking the best of, as I told before, best of Lagrangian and Euclidean. Okay, so as I notify you the problems with Lagrangian and the Euclidean. Okay, so here when you are seeing this figure, see, you are having the change in location of the mesh, which means your mesh element is changing, mesh point is changing, as well as the material is changing. So when you are using this alley, you can know the real material deformation because the material is free here. It can move anywhere. It does not depend upon the point. So you are getting a best of this Eulerian, which is this Eulerian. You will have the higher. You can accommodate the higher strain. So you are getting a best of this Eulerian. And the second one is the mesh displacement. So this is the best from the Lagrangian. So when you are going for displacement of the mesh, again it supports the strain, the largest strain. See, if you take a tensile test or a hard deformation compression test or any test, there the strain will be very, very less. But in friction stir welding, like as I showed in one of the picture, the material has to flow around the tool, so you have a lot of material needs to be rotate, no move. So you need both goodness from this Lagrangian and Eulerian. So this joining will helps you because it won't leave any of the phenomena of the material flow. And the second one is in alley, since the material point is moving and there is some strategy you can go for remeshing. So in one of my slide I can show that. Okay, here you can find that this Tirzone region alone I gave the alley, and for the tool I gave Lagrangian because in the tool it is a rigid tool. This tool does not deform or it may deform very little bit. So I'm not talking about any strain or distortion. Okay. Oh, sorry, I think I made a mistake there. No, it is correct. It is correct. So it is not showing any more distortion. So when it is comes to this Eulerian workpiece, here you can find this region does not have more strain. This is an undeformed region. This is the only region going for the higher strain. So I only use alley here. That's why I'm not using alley here and here. And the second one is this region is going to connected with the Eulerian workpiece. So you will have different nodes here and you will have different nodes here. So at each incremental steps or at each tool rotation, the mesh points will be remeshed in order to support with the Eulerian here. So in this way, I made my model. Did I answer your question?
Yes, sir. But, one more thing, sir. You have mentioned about remeshing.
Yeah.
So, is it only possible in ALE or is it possible in Lagrangian also?
I think remeshing in Lagrangian. I think it is moving along with the mesh points. I think there is no record of remeshing there.
Oh, okay, sir. Okay, sir. Just asked because
Sorry,
you
actually,
mentioned about remeshing.
yeah. It is not in the Lagrangian. It is not in the Lagrangian. Okay. And you see, if you go for a remeshing strategy or remeshing algorithm, you will have a higher computational time. So better go to some of the model ALE or CEL. Better go for CEL. You will have a less computational time, and the remeshing is not a problem over there.
Okay, sir. Okay, sir. Thank you.
Okay.
Sir, I will read out the questions in the chat box.
Okay.
One question from S. Venkateshan. He's a professor in Vinayaka Mission College, Salem. So, which is the best FEM tool to validate and analyze the welding joints, especially FSW?
Sorry, can you repeat the question?
Which FEM tool is best for validation and analysis of friction stir welding process?
Okay, to my personal experience, Abacus. But all the other tools are also equally capable, but Abacus have a lot of capabilities. And as I told in one of the slide, when you are going for Abacus, you can use your own, you can write your own photon program to represent the loading conditions, to represent the material model, to represent the contact condition. So whatever you want, if you know a photon language programming, you can do whatever you want. But if you go for a console or ANSYS, I'm not sure that, I don't know about ANSYS, but console and what are the software, what I used is the Comet. It does not have much capabilities on that. So all the tools in terms of tools, it's like a product, like someone have a Reynolds pen, someone have another pen, so everything is going to write the same thing. It's kind of the answer. But in terms of some capability, some features, Abacus is good.
Okay, sir. And that is a request from Shivaraj, sir. Can you switch on your video so that we can see you?
Okay. I thought I'm in video mode. Okay. I'm missing out, but in a very dark mode. Yeah.
Yeah.
Hello, sir. How are you? Okay.
Fine, Sabri.
Okay, sir. Any more questions?
So, sir, good evening.
Yes.
Sir, what is a subroutine?
Okay, so you are asking what is subroutine or what is the subroutine we need to use?
Yes, sir. Yes, sir.
Okay, so I will tell both. So subroutine is nothing but like it's a program. Like you know the C program or some program. It is just a program. In that program, you can use some equations and some parameters, values, or some kind of models. You can write it in that in a programs, and that program can be used or coupled with your Abacus model or whatever the model, whatever the tool you are using. So, for example, if I am using a U-hard subroutine, so U-hard subroutine is a subroutine, nothing but it's a program which represents how the hardening of the material will happen. So if you take a tensile stress and curve, after yield point, the curve will increase. That curve is called the strain hardening portion. So as the strain increases, you are having the strain hardening there. So in some of the cases, this conventional model which is available in the software is not capable of representing that hardening behavior. Okay, so what you are going to do is you are going to do additional features. Okay, additional feature, that is the subroutine. This subroutine will be run in a Fortran language platform, and it is coupled to the software. And every time it will, when the material calculation begins at each increments, it will go to the Fortran and know about the material, and it will come to the simulation. Then it will go to the Fortran, know about the material, come to the simulation. So in this way, it is coupled together so that you can do that.
Okay, thank you.
It is very simple. Like in a simple example, I can say like you are buying my bike and you are doing a modification according to your need. So it's in a similar way. You are having an abacus. It is not giving some features. So you are adding a subroutine to support that feature. That's it.
Okay, thank you.
Sir, I would like to ask a question that is an extension of what you have answered. Whether this subroutine files has to be defined by us, or it will take as it wants, sir.
No. It is purely by you. It is just in a way I can say that it is just a blank Word document or blank notepad document. You need to write from the starting to the ending. What is the boundary? What is the governing equation? What are the sub-governing equation for each parameters? And at what time that parameters needs to be used? So these are the things should be present in a subroutine.
Okay.
Maybe I can. Yeah. Please tell me.
Is it necessary to define this subroutine, or it is an optional one to get an additional result from the software?
It is an additional one. As I told before, I guess you had some knowledge in abacus, okay, and some material model. You have different material model: perfect plastic, perfect elastic plastic, damage model. So these are the different models. Why this different model is there? Because these different models are not sufficient to completely give the material behavior. So in order to give all the stuffs about the material, everything about the material, we need a subroutine. So I think now I'm going to show a subroutine to you which I made. I will share that to you. This is not a subroutine for material modeling. This is a subroutine which I made for modeling of a fusion welding process, an arc welding process. In this, you can see that. Are you seeing my screen?
Yes, sir.
Yeah. So, what is a subroutine? What are the various parameters you are going to use as? What are the variables and everything needs to be assigned here. Okay, and then it needs to be explained in each steps. For example, here this is the time, represents that the welding time at each increment. This is the heat source moved, the location of the heat source, where it is in, for example, at time t+1, what is the x value, y value, z value we need to give, and what is the efficiency, what is the power, and how the heat source is moved. It is moving in a straight line, or it is rotating, or it is curving, it is rotating along a path or anything. And then this is the heat flux equation, how the heat flux is formed. It is based upon, so this is the shape of the heat flux, whether it is a double ellipsoid heat source or it is a conical heat source. So you need to give everything here. So at each time of simulation, at each time of your heat source movement, it will come to this program and it will see how it needs to behave. Then it will go back to the simulation. Then it needs to come here. So in this way, it will work.
Yeah, okay, sir. Thank you.
Okay.
Thank you, Sabari.
Yes.
Yeah. Thank you very much for your excellent presentation on modeling and simulation. I think many researchers, those who are doing, they got some idea how to do modeling and simulation, especially on FSW. And so with this, we'll close this session. And once again, I thank Dr. Sri Sabari. I don't know, so you are there. The time is, what is the time now?
Now it's 11:50 morning.
Okay, it's fine. So it's we are 5 hours running behind. Am I right?
Yes, 4.5 hours.
Yeah, 5. Okay. So anyway, thank you. Take care. And how is Corona and all there in Portugal? Yeah.
Here it is okay, sir. Now we completed the second wave. We are waiting for third wave.
Third wave also will come.
Maybe, sir, because now when the last 18th, they opened everything, so we are expecting a new one.
Oh.
But I don't know. Yeah.
Okay, take care. So we are in the middle of the second wave. So we don't know when the second wave will come to an end. And we also hopefully know it's, the third wave will not come. Anyway, so take care and we will meet on some other occasion. If time permits, you can also stay back for the next lecture by Dr. Gaurav Rao. Maybe it's after a 10 minutes break. So now it is 4:20. I request the participants to have a cup of tea at your place and join again at 4:30. 4:30 we'll have the next lecture by Dr. Gaurav Rao, a scientist from Naval Materials Research Laboratory, DRDO, Ambernath, Maharashtra. So he will be delivering a lecture on friction stir welding and friction stir processing related to the defense application materials. So I request the participant to rejoin at 4:30 to start that lecture. Thank you.
Thank you, sir.